David Smith here with one more Flip Classroom math video in the rain. 3 tips before we start. First, you can speed up or slow down the playback if that helps you digest the content. Second, you can pause the video anytime and catch up with your notes. Lastly, you could turn on the captions and watch my words go by on the bottom of the screen. Today's lesson covers using the second derivative to figure out this concept called concavity. And so concave up means that the curve is facing up. Concave down means that the curve is facing down. And then finally, an inflection point is where a concave up meets a concave down section. So let's get started and take a look at that. If the second derivative for some value of x is positive, greater than 0, then at that portion of the graph, f of x is concave up. So that means the curve is facing upward. If for some x, the second derivative is negative, is less than 0, then it means that portion of the graph is concave down. Okay? So this is what the second derivative is telling us. Finally, for a certain x, if the derivative, the second derivative of f of x is 0, it means we have a possible inflection point. And that's where if we change concavity, so if this point that equals 0 is surrounded by a concave up on one side and a concave down on the other side, then that's what we call an inflection point. So let's take a quick look at a graph that shows these 3 things. Check this out. This is f of x equals x to the third. This is the mother power function, the mother cubic function. And so for this section of f of x, it's concave down. And for this section, the curve is facing upward. This point here is where the concave down and the concave up portions meet. So that is an inflection point, okay? So if you were to test, write your second and your third derivatives and test points along here, you would find your second derivative would always be negative here, concave down. You'd find your second derivative would always be positive for these values of x, and it would be concave up. All right, let's get started with this idea of concavity. We're going to go through our usual sequence of events, figuring out what we can do, what we can use differential calculus to figure out about a function. So here is our function. 2x to the 4th power minus 4x squared plus 1. So first step here, let's call that 1. Find out where the function is increasing and decreasing. So before I let you go, let me summarize what you do. You first take the derivative, the first derivative of the function, set it equal to 0, and solve. And then test those boundary points on a number line to find out where the function is increasing and decreasing. So pause the video and do that. All right, so here is my f prime of x. I went ahead and took the first derivative of that. So I end up with 8x to the third minus 8x. That's my second derivative. Now I need to solve this by setting it equal to 0. So my first step here is going to be to factor it out so I can use my product rule. And so I factored an 8x out of both terms. That leaves x squared minus 1. This is a perfect square. This is just x plus 1 times x minus 1. So I wrote that out here. So that's my factored form. Now I have 3 terms that I can set each one equal to 0 and solve, which I did here. 8x times x minus 1 times x plus 1 equals 0. I get x equals 0 for one solution. I get x equals 1 for the next. And then I get x equals minus 1 for the last solution. So now I drew my number line here with these important points. These are the points at which the function changes from increasing to decreasing. Finally, now I want you again, pause the video and figure out what's happening to the function in each of those intervals. Go ahead and pick some values to plug in, do the math, find out if the first derivative is negative or positive. Okay, I figured out kind of a little bit of a shortcut for this step where there's extra math we don't need to do to get what we need out of this analysis. So what I did is, you'll recall I have my number line here with my important points where the concavity changes, where it goes from increasing to decreasing. And what I did is I just put in some points negative 2, negative 0.5, 0.5, and positive 2. And I put those into the second or the first derivative to find out what the sign is, to find out whether the function is increasing or decreasing. So when I did my plug-in step for f prime of negative 2, I noticed that I have 3 negatives here. So it doesn't matter what the number is, the result is going to be negative if I have 3 negative numbers times each other. Whatever that number is, it's going to be negative. Same thing for f prime of minus 1/2. Minus 1/2 is in here, so I'm trying to figure out what the function is doing there, increasing or decreasing. And this time I only have 2 negative signs. The other 2 terms that are being multiplied are positive, so that means the sign of that's going to be positive. So let's add these to our thing. We have decreasing, increasing. Then finally f prime of positive 0.5, which is between 0 and 1. That gives us only 1 negative in our multiplication chain. So that means the result is going to be negative. So I can put a minus sign here over that interval. And then lastly, f of 2, which is out here beyond the 1. All the numbers that are being multiplied are positive. So the result is positive. So I have a positive there. So now I know what's going on. I can sketch roughly the wavy function over my number line. I'm decreasing until here, and then I'm increasing. So I can go like this, and then I'm increasing till 0, and then I'm decreasing, and then I'm decreasing until 1, and then I'm increasing. So there's my rough graph of what the function is doing. Okay, let's do the next step. And this is where we're going to use what I threw up on that first board, i.e. using the second derivative to talk about concavity of the graph. So check this out. I've got my f of x here, original function here. I've got my first derivative here, which we used to determine where the function was increasing or decreasing. Finally, now what we have to do is take the second derivative and use that to determine concavity. So pause the video, take the second derivative of that, and come back. Okay, here's my second derivative. This is a straightforward derivative calculation. I just did the power rule on each of these terms, and I get 24x squared minus 8. So that's my second derivative. Now, set that equal to 0 and solve for x. All right, so this is best solved by just factoring an 8 out of both terms there. I get 8 times 3x squared minus 1 equal to 0. I'm going to take this term here and set it equal to 0 because the 8 doesn't matter. There's no x's by it. So 3x minus 1 equals 0. 3x squared minus 1 equals 0. That reduces down to x squared equals 1/3. Take the square root of both sides. I get x equals plus or minus 1 over root 3. Now we have this convention in math. We like to rationalize the denominator. So I converted 1 over root 3 to root 3 over 3. I just multiplied top and bottom by root 3. It's just a form of 1. But that gets the root out of the bottom. So here are my solutions, plus or minus root 3 over 3. I went over here to my number line. I graphed the 0, the minus root 3 over 3, and the root 3 over 3. Now I just need to test my derivative to find out if it's positive here, if it's positive here, positive there, positive there. Okay? Actually, there's only 2 intervals I need to test. I put my 0 on here, but 0 is not a condition that we're worried about because 0 does not make this equal to 0. So really the only 2 points we need are these 2. Okay, so pause the video and do that. Pick some values for x and test that out. Okay, so check this out. I just did my f double prime of negative 1. That's going to be a little bit further to the left. I did it of 0, which is smack dab in the middle of these 2. And then finally I did f double prime of 1. Took the second derivative of 1 to test that interval out there. And check it out. The second derivative of negative 1 gives us 16, which is positive. So we know the function is concave up there. Then the second derivative of 0 ends up being negative 8. So we know that the function is concave down there. And then finally, the second derivative of 1 ends up being 16 again. So we know it's concave up there. So now we can write this as interval notation. So pause the video, do that. Okay, so here's the interval notation. Concave up from negative infinity to negative root 3 over 3, combined with union root 3 over 3 all the way to positive infinity. And then concave down for in between those two, root 3 over 3, minus root 3 over 3, and root 3 over 3. So that specifies all of that out for you. Action. All right, so I summarized everything we have so far here. Here are my turning points. Here are my inflection points. And I want to point out that on the last board, I had the negative sign on both of these. Remember, one of these is positive, one of them is negative. So I fixed that there. And then just for ease of graphing sake, I converted root 3 over 3 to 0.58. So this is minus 0.58, or roughly minus a half, and this is positive, again, roughly a half. So now that you have these 5 points and this information, you can sketch a complete graph of this function. So go ahead, pause the video, give that a shot. Okay, I thought it might be helpful to see how I construct a graph. So when I first did draw my axes, I looked at my points. I noticed that these are all less than 1. So 1 is going to be one of my biggest points on here. I took a look at these and I've got -1, and I've got 2 positive ones. So what I did is I graphed these 3 points first. I went to -1, -1, then there's 0, 1, then there's 1, -1. Then I went ahead and folded in these 2 points. I have -0.58, positive 0.111, that's roughly where that would be, and then also 0.58, 0.111, there's where that would be. So now what I want you to do is, once you get that in your notes, pause the video and take a look at where it's increasing, decreasing, and where it's concave up and concave down, and go ahead and connect those lines in a good graph. Okay, let's see how you did. Now watch me go. I know that it's decreasing all the way to -1, -1, and then it turns around to increase. And then it changes. This is an inflection point. So it's going to change from gently curving up to gently curving down there. And then this is another place where it changes from increasing to decreasing. So that's going to curve back down. It's still concave down until this inflection point, where it's going to gently change from being curved down to being curved up. Then it's going to pass through that turning point and go on up forever. So let's sketch that in. Decreasing, turning point, inflection point, turning point, inflection point, turning point. So what would be interesting is go ahead and put this function into Desmos or your calculator or some kind of graphing tool and take a look at how that graph looks. It's going to be nice. Should match all this. And if you use your trace function or whatever function you have so that you can get to these various points, you should be able to see that indeed they are the values that we've put there. Thanks for watching. Just before you go, make sure to write down any questions that you have so that you can bring them to our next class and get them answered. Also, remember that you can watch the video again if you want to deepen your understanding. Finally, if you enjoyed the video, please click like or subscribe.